Hello everyone, welcome back to the another session in design and analysis of algorithms. Topic name is backtracking using recursive approach. This topic you will find in third unit as topic number 8. So this video will be going to cover about two things, that is backtracking with two different approaches. The one is recursive approach, the other one is iterative approach. We'll take some example and we'll find the solution using recursive and iterative. Now let's get started. So basically, let's get a clear idea about what is backtracking and what we will do in backtracking. So generally, backtracking is a modified depth first search of a tree. Now, so backtracking algorithms determine problem solutions by systematically searching the solution space for the given problem instance. So let's assume some problem. Now I'm taking some problem which is sum of subsets. I'll explain you what is this problem, then we'll find the solution using backtracking. Now let's take some objects which are n is equal to 4. Now the aim of this problem is what, or the expected solution is what? I have to take any subset from this set where the balancing capacity is what, 31. If you put all these items, then that will be go beyond of 31, that is more of 31, but I want only sum of subset. Now if you see this whole set, if you add 11 plus 13 plus 24 plus 7, it will be greater than the m value, correct? So what I have to do is I have to take only the sum of subset. That subset can be 24 7 or the subset can be 11 13 and 7. So out of your 4 objects, you can place any 2 objects or 3 objects where the capacity. Now let's see, the formula for sum of subset is what? Wixi, the weight of the object, plus the other object weight, that will take I is equal to 1 to k. When you have one object, that object weight has to get included with the other object where the capacity should be less than or equal to m. So this is what the idea of sum of subsets. So we'll find the solution using backtracking, recursive approach and iterative approach, and we'll draw a state space tree. So this search is facilitated by using a tree organization for the solution space. So basically backtracking is a procedure where by after determining that a node can lead to nothing but the dead end, we go back to the backtrack to the nodes parent and proceed with the search on the next child. A backtracking algorithm need not actually create a tree. Rather, it only needs to keep track of the values in the current branch being investigated. This is the way we implement backtracking algorithm. We say that the state space tree exists implicitly in the algorithm because it is not actually constructed. Now let's find the state space tree for the given problem. So if you consider the given problem in 24, 7, right? Now we'll construct a state space tree to find the solution space for the same problem. So what we'll do is using backtracking approach. Now let's see recursive and iterative both the algorithms, then we'll come for this state space tree to trace it. So basically what is recursive backtracking algorithm? Now we'll start, as far as backtracking is concerned, the state space tree will works with what? DFS, depth first search. That means you will be starting with the node and you will be taking the part of the solution, considering that is the solution. Now, so after you find the solution for this, now let's see, there is solution is no solution we found in the first node. We are just making the solution with an assumption that x1 item can get added. So once x1 get added, that means the other side is x1 equal to 0. So actually we will not write this one because it is not BFS, it is DFS. We'll go depth wise. Okay. So that means x1 is added. So the other node will get created and x3 is added. the other node is get created, and we'll go to dead end of the state space tree. Once our solution gives beyond of the range what we are expecting, then we will backtrack the solution and to all the parents, and will come to the child node of the root node. So this is what actually backtracking ideology. Now the recursive backtracking approach is what? For each x of k, that means for each object of k, we will be going to call the function which can be happened repeatedly, that finding the path from the parent node to the child node. So this is what happens in recursive. What we will be going to execute recursive call, we'll call the same function until it performs, right? Now let's see iterative. Iterative is what? We'll take one loop until it becomes 0. If k is not equal to 0, now let's take that I have items of n is equal to 4. That means my k value will lies in from I is equal to 1 to k, where wi xi plus wk plus 1 less than or equal to m. That means I value will start with what? N to k. So this n value is 1. Initially it is 1. That means 1 to k. So till k value is not equal to 0, we'll be going to run the loop. So what is this loop? This loop is what? Will include each object into the solution. Now we'll trace this. So in the sum of subsets, I have taken 4 objects, right? So n is equal to 4, and those items are 11 weights. 11, 13, 24, 7. To balance the weight m is equal to 34, which weight I have to consider? So initially I am taking there is no solution. The 0 indicates no solution is added, and the total, when the no solution is added, your capacity is what? 31. So now, so as it is a depth first search, I have to go to the till dead end. Now I am adding x1 solution. It indicates x1 is equal to 1 indicates that I am adding 1 solution. So when I add 1 solution, my solution from null to it goes to 11. Now this 11 will get subtracted from the whole weight, which is, so you have to take this assumption 0, 31 is initial state. The 0 will become with k value is equal to 1. So when k is equal to 1, that is what? x1 is equal to 11. And your capacity m value will get decreased with what? M minus wi xi. M minus wi, weight of the first object, is what? 11. M minus 11, which is 31 minus 11, which is 20. So this is 20 and this is 11. So what if happens if included with second object? Now already it is there in the first. Now second I am including 11 plus 13. The weight will become what? The weight will become 24. So this 24 weight will get decreased with this, correct? 24. Now, so from 31, we'll deduct or we'll subtract 24. So it will be 7, correct? Now, so 11 and 13 are part of the solution, and 7 is what? Leftover weight, what you can still consider. Now, what if happens adding with x3 object? That is what? 24, x3 weight, which is 24. So 11, 13, 24, but it is not the solution, correct? If you take this kind of solution, it takes 2 power n comparisons, correct? My n value is what? 4. So total you will get 2 power 4, which is 16. Now this is what your last node. So exponential time complexity it will take. And keep this in mind, all these are not the solutions. The solution is what? When the subset will balance this weight. That is the solution. So we will be going to take a bounding function. So bounding function is nothing but it's a condition. It's a condition to cut the solution into optimum. So now what we will do is, now look at this 12th node. So how I can generate this 12th node? By adding the third item weight. If I include this third item weight, it becomes what? It goes beyond of greater level of m. It goes. beyond of 31. So it is not required to add into the solution. What I'll do, I'll apply bounding function. What is bounding function? Bounding function is when the weight of the object adding with the subset of the object will go greater. It is what constraint what we have to maintain. When it goes beyond of this capacity, will kill this node. Saying that, applying bounding function. So what is bounding function? It is a condition what to be maintained in the algorithm. Now this node will get killed. So now what happens? When I kill this node, there is no extraction, there is no e-node generation from this node. Then where we'll go? We'll backtrack. We'll backtrack to this object and we'll delete this x3 and we'll come to this side. Now what happens if x3 is not included? So x2 is included, x3 I don't want to include it. So what is, I have the option x4. So what happens if I include x4? Balance, weight will get balanced because the leftover weight is 7 and the last object weight is 7. So it is the perfect solution. Now we'll not stop up to here. We'll again go backtrack till you find all the comparisons. So this is what actually backtracking approach or generating the state space tree with recursive and with iterative. Thank you all.